So now we know that the small signal gain is the same, no change. And what was the main motivation to come to this structure? The output swings, right? So let's compute that and check. So let's quickly find the input common mode range and the output swing limits, and then we'll put it in unity feedback and see what happens. Okay. So let's quickly do that. So help me now. If VICM keeps reducing, sorry, VICM, I'll mark it here. If VICM reduces, which transistors can go out of saturation? Yeah, okay, I'll have to replace this with real transistors. This is M0 carrying a current I0. Similarly, this will be PMOS transistors. Just give me a second. Okay, let me call this M9, M10. So the current is this. Yeah. So which transistor goes out of saturation if VICM reduces? M0. So what is the minimum you can have? It is the gate to source voltage plus VDS. So the minimum it can go is VGS of M2 at a current I0 by 2, that is fixed, plus the overdrive of M0 at a current I0. Fine. Now similarly, if I keep increasing VICM, which transistor has issues? Let's say this is VP6. Which one? M1 and M2 will have issues. Gate voltage is increasing. Oops. Right? This fellows will go out of saturation. And what is the maximum the gate voltage for an NMOS transistor can go? One threshold above the drain. So let's try to find the drain voltages. Let me write it here. This is let us say VD2 plus VDH2. Fine. Let's try to find the drain voltage. So these are the drain voltages, VD1 and VD2. So what is VD1 and VD2? What is deciding the voltage here? Which one? Yeah, remember that once again the currents in this branch, let me mark it again, this is I1. Okay, let us say this branch is biased to be at a current I1. So which means the VGS of M3, M4 is fixed, and whatever bias voltage you apply plus a source to gate voltage of M4 or M3 will decide the drain voltages there. Right, so if I mark it here, this is source to gate of M4. So this is equal to VB4 plus source to gate of M4 at a current of I1. So then I can calculate this. This is VB4 plus source to gate of M4 at a current I1 plus VTH2. Okay, this is fine. So then let's compute the output. At the lower end, if output keeps dropping, which transistor can go out of saturation? M6. So what is the minimum the drain voltage of NMOS transistor can drop to? One threshold below the gate voltage. The gate is connected to VB6. So this will be VB6 minus VTH6. Okay. Similarly, if Vout keeps increasing, which transistor can go out of saturation? M4. Again, logically, if Vout increases, Vout is the drain voltage, so one of these two transistors will go out of saturation. So if drain voltage increases, PMOS transistor will have issues. So the maximum the drain of a PMOS transistor can go is one threshold above the gate, so that is VB4 plus mod VDH4. Okay. Cool. So now let's try to do the same comparison as we did for our telescopic cascode. and we'll do the same fair comparison. So we'll try to design this OTA so that output swings are maximized. Okay. So to find the maximum output swing, I should look at the minimum of VB6 and maximum of VB4. Clear? So let's calculate that. No, overdrive is not in the sense, see, this is VDD minus VSD, isn't it? The source to drain voltage is not something that is fixed. Okay. Remember that the drain voltage anywhere should be fixed by some kind of negative feedback. Here the negative feedback action is coming because you are biasing with some fixed current, and then your gate voltage is connected to some voltage here. So which means the source voltage will adjust automatically to maintain the drain current, to maintain the current. Okay. So this is same thing as if I push in a current and do this, you can't expect this voltage to be set. Okay. The idea is the minimum this can drop is something overdrive voltage, but that will happen if you connect this to the appropriate voltage. Okay. Biasing of M? Yeah. Why do you think that is a problem? Oh, sorry. Yeah. Oh, yeah. Thank you. This is probably VB10. Oh, thanks. Yeah. Hopefully here we didn't use this, right? Yeah. Thanks. Yeah. Okay. So now let's try to find the minimum of VB6. That is this voltage. So if minimum, let's try to do that directly. VB6 is essentially VGS plus VDS. Fine. So what is the minimum of VB6 then? It is the VGS which is fixed plus the minimum of the drain to source voltage of M8, which is, so we should be able to write it directly now. So this is VGS of 6 at a current I1 plus overdrive of M8 at a current of so let's calculate this. This will be, this is the minimum Vout can go is this voltage minus VTH6. So if I subtract VTH6 here, this is essentially overdrive of M6. Again, shouldn't be surprising. Once again, the minimum Vout can go is 2 drain to source. So that is 2 overdrive voltages. And again, that is being possible because you have free control on the gate voltage. Okay. So this I will directly write. This is overdrive of M6 at a current I1 plus overdrive of M8 at a current. Great. Then let's try to find the maximum of Vout. So that depends on maximum of VB4. So let's write it. VB4 is this fellow. Again, if you look at VB4, it is the supply VDD minus the source to drain of M10 minus source to gate of M4. Okay. Fine. So then what is the maximum VB4 can go to? For this to reach the maximum value, these two drops must be as small as possible. Correct? Now VSD4 is fixed because the current is fixed. So what is the only thing that can go minimum? The source to drain of M10. So can you directly tell me what is VB4 max? VDD minus the minimum you can drop here, which is source to drain of overdrive of M10. Overdrive of M10, okay, at a current I0 by 2 plus I1 minus source to gate of M4. So now I can substitute this maximum value for VB4 here and find the output maximum. So the output maximum is this VB4 plus a threshold voltage. So which means I will be adding plus mod VTH4 So you obviously have minus VSG plus VTH, that is the overdrive voltage. So what is the Vout max? VDD minus, I mean from here can you tell me directly, you should be able to tell ideally, VDD minus overdrive of M10 minus M4. That is again being possible because you have free control on VB4. If you connect VB4 to this value, Vout can reach that. VDD minus overdrive of M10 at a current I0 by 2 plus I1 minus overdrive of M4 at a current of I1. Okay. Okay. So now let's take the same example we did in the start of the class. So I'll erase this. Is this fine? I mean, I try to write the maximum and minimum for VB4, VB6 directly from the circuit. So if you have doubts, let me know. I'll clarify. We will see. I mean, see, now we have two currents, right? I0 by 2, I1. So you can have again three possibilities: I0 by 2 greater than I1, I0 by 2 smaller than I1, or equal. In the next class, or today we'll not have, in the next class we will see what can determine that. Okay, so then I'll erase this for now. We'll just stick with the numbers here.
So basically
VB6
is not completely analysis.
Yeah, I mean, you one thing is known for sure, right? The current is I1, correct? But VB6 can be anything. Once I fix I1, only the gate to source voltage is fixed, right? If you connect VB6 to some value, the source voltage will adjust automatically so that the VGS is of the required value, correct? I mean, think of it like this: we have a feedback here, right? That is, if let us say the gate voltage increases, technically the current will tend to increase. If current increases, this voltage also increases. That will keep the VGS constant.
So which means Vout is not really linked to VB6. The minimum Vout is actually linked to I1.
Yeah, I mean, it is linked to both, right? VB6 depends on VGS of I1. I mean, when we say minimum of Vout, it is overdrive of M6, but it is at a current of I1, correct?
So,
It depends on that also. I mean, the question is, I mean, the idea is, right, you can have the same overdrive voltage for multiple values of current by choosing appropriate width, isn't it? I mean, I can have the same overdrive voltage, but I can have different values of current by changing width, right? So that's not a problem. So that's why we're just looking at the overdrive voltage. Okay.
My number is that overdrive voltage is fixed once the current is.
Yeah, of course, yeah. But you can design for a particular overdrive voltage. It's usually the other way around, right? Overdrive voltage also depends on the sizes, isn't it? You can choose a particular, I mean, the same GM by ID technique we saw, right? You decide a VGS, and then you choose, like appropriate current density. That will give a current density, so which means you can do. Okay, so let's take the same example we did. So the numbers we took was supply, maybe I have to make some space. Supply is 1.8 volts. The overdrive voltage was 50 millivolts. Threshold was 400 millivolts. So the VGS was 450 millivolts, correct? So now can you quickly compute the numbers here? So what will this be equal to? Assume all overdrive voltages are same. So this is 1.8 minus 50 millivolts. This is how much? So similarly, what is this value? Two overdrive voltages. 0.1 volts. So so we need to find VB4. So let's find VB4. What is this value? It's 1.8 minus 0.05 minus 0.45. How much is this?
1.7.
No, it's not. 1.3 volts, right? So let's use that here. This is 1.3 plus 0.45 plus 4. How much is this? How much is this? This is good. And what is this then? VGS is 0.45, overdrive is 0.05. This is so once again the assumption is we are trying to put it in unity feedback, which means the input common mode and the output both are equal. So I have a minimum set by VICM which is 0.5, a minimum set by Vout which is 0.1. So what will be the final minimum you will choose? 0.5 volts. That didn't change. Let's look at the maximum. I have 2.15, 1.7. What will you choose? 1.7. Okay. So now you clearly see I have a swing from 1.7 to 0.5 or 0.5 to 1.7. So that's about 1.2 volt of effective swings you can have in a 1.8 volt supply, which is significantly better than what you had for the telescopic cascode. So this is one of the main advantages in using folded cascode over a telescopic cascode. So let me mark it here. So I will say better swings in unity feedback. Now, not just that, if I look at just the absolute minimum for Vout, how much is that? 0.1, right? That is 2 overdrive voltages is the minimum Vout can go. Now, let's look back at the telescopic cascode. Okay, let's say, yeah, this one. So, what is the minimum we can go? It is overdrive of M4, overdrive of M2, overdrive of M0. You have 3 overdrive voltages here because you have 3 NMOS stack at the lower end. So here the minimum is slightly higher by 1 overdrive voltage, right? So even if I look at the absolute minimum for Vout, folded cascode wins. Okay, so I will say better Vout minimum. And another interesting thing to note is this. What can you say about the maximum of the input common mode voltage? What is the maximum it can take? 2.15 volt. What is my supply? So this is actually, this can be greater than the supply itself. Okay. So we can have an input common mode which is equal to supply or greater than supply also. So even if the input common mode in your final negative feedback circuit, or I mean this unity feedback not, but let us say you have some other feedback, whatever. Right. If the input common mode is equal to the supply also, it's pretty good. Okay. And the input common mode is equal to VDD when I have an NMOS input pair, that is when I have an NMOS input for the transconductor, right? Now remember, I can have a similar circuit by just replacing an NMOS transistor with a PMOS transistor. So which means I can make a same folded cascode op amp by using a PMOS input differential pair. Now can you take a guess what will be the VICM condition if I have a PMOS input pair? I mean, for a folded cascode, we saw if the input pair is NMOS, the VICM can reach VDD. Similarly, can you guess what might be the advantage for VICM with PMOS input? It will go, I mean, it can go actually lesser than 0 or it can take 0 volts. So in fact, let us say if you want to design what we call rail to rail op amp, wherein the input common mode can take all the way from 0 to VDD, you kind of try to use a combination of both NMOS and PMOS input in parallel so that both of them can use. So what I'll do is I'll give an exercise for you, or if you have time, you try to sketch now. Sketch the PMOS input folded cascode. Okay. You have a couple of minutes, try to sketch it. At the at the end of the class I'll quickly draw. So please take right now try to sketch a PMOS input pair folded cascode op amp. I'll show the NMOS equivalent circuit here. The idea is there is no point in by-hearting or memorizing circuits, right? You should understand what each transistor is doing, the role of everything. So just try to replace this with every transistor you try to replace with a PMOS and try to sketch now and see if you can get it. So I'll just draw one half of it and you can figure out. See, I have here an NMOS input differential pair, so I should replace it with the PMOS input differential pair. Fine. And here the common source terminal, I have a current source to ground. Here what should be the equivalent? Current source to VDD. First let's start with ideal current source, it's fine. Then this is the main differential pair that is converting the voltage to current. Again, the idea is now in a folded cascode you want to give this to current buffer, but this is a PMOS input, so you should give it to source of which transistor? An NMOS input or NMOS current buffer. So you have, let us say, an NMOS like this. So let us say one goes here, the other goes here, okay, and that is M3 M4. This is what I have drawn. So the drain of this current buffer is the output, that is said. So here at the drain I have connected an NMOS cascode current source. Here I should have PMOS cascode current source. I'll leave that for you to work out. So here you should have a PMOS cascode current mirror. So once again you will have two options, either to use this high swing cascode or this low swing cascode. So both of them you should be able to sketch. And what should come here? So what should come here? Yeah, ideally it should be what element? Yeah, not NMOS in the sense like in term should be a current source too. Okay. So if you understand what each transistor is doing and what the role of each fellow here is, should be able to sketch the circuit. So like I told, there is no point in trying to memorize or by heart circuits. That's not going to help. Okay? Because I can make multiple combinations by changing NMOS to PMOS, PMOS to NMOS. So if you don't understand what the role of the transistor is, it will look like completely different circuit, but at the core of it, it will still be the same. So I'll stop here. We'll resume.